Here's a pattern that plays out repeatedly in system design rounds. 7 years of backend experience. Leak code rating in the top 15%. Clean, readable code. He passed every coding round without breaking a sweat. Then came the system design round. The prompt was simple on the surface. Design a customer support assistant for an e-commerce platform. He immediately went to work. Load balancer, REST API, PostgreSQL, read as catch. Textbook stuff. Beautifully drawn. And he got rejected. Hard rejected. Not a close call hire with reservations. A straight no. Why? Because the interviewer was expecting him to recognize that this was an LLM agent loop problem. The assistant needed to call tools, check order status, handle multi-turn context, and stay within a token budget that maps directly to operating cost. He designed a stateless CRUD system for a problem that required stateful agent orchestration with cost constraints baked into the architecture. That gap, that single blind spot, ended a 7-year career story at that company. And here is what I want you to understand before anything else. This is not an isolated case. This pattern is now the majority rejection reason I see at staff and senior levels. By the end of this lecture, you will know exactly what that gap looks like and how to close it. So why is this pattern accelerating so fast? 3 years ago, a candidate who could write clean, efficient, well-structured code had a real edge. That edge is gone. GitHub Copilot, Cursor, Claude. These tools have compressed what used to be a 2-hour implementation task into 20 minutes for almost anyone. Companies know this. Interviewers know this. When implementation skill is no longer a reliable differentiator, the bar shifts upward. And it shifts to architecture. Here is what I see happening in real hiring panels right now. The implicit scoring rubric has changed. In 2023, roughly 60% of your score came from implementation correctness and maybe 40% from design quality. In 2026, that ratio has inverted, and then some. Architecture judgment, specifically the ability to reason about AI components, cost trade-offs, and failure modes under ambiguity, now accounts for the majority of the signal interviewers are extracting from you. Think about it from the company's perspective. If an AI tool can help a mid-level engineer write production quality code, what they actually need to pay a premium for is someone who can decide what to build, why to build it that way, and what happens when it breaks at scale. That is the new filter. And if you are still preparing with the old filter in mind, you are optimizing for a game that has already ended. But here is the thing, once you know the new rules, catching up is faster than you think. Let me be specific about what you will walk away with after this lecture series, because I hate vague promises as much as you do. Here is the concrete outcome. You will be able to structure a complete AI-era system design response within 30 minutes and hit every dimension a 2026 interviewer is scoring you on. What does that mean in practice? First, you will have a repeatable framework for integrating AI components into your architecture, not as an afterthought, but as a first-class design decision. That means knowing when to use a RAG pipeline versus fine-tuning, when an agent loop is overkill versus necessary, and how to draw the boundary between your orchestration layer and your model layer. Second, you will be able to estimate and defend cost. This is the one that surprises most candidates. Interviewers at AI-first companies now explicitly ask how much your design costs to run per million requests. If you cannot answer that, you signal that you have never operated an AI system in production. Third, you will know the scalability failure modes that are unique to AI architectures, things like token budget exhaustion, context window overflow under load, and latency percentile collapse when your LLM call is on the critical path. These are not hypothetical. I have dealt with every single one of them in production. Let me show you what the full checklist looks like, and we will go deep on each one across the rest of this series. Let me show you something concrete right now, because abstractions only go so far. Here is an actual interview question that was common in 2024. Design a search autocomplete system for an e-commerce platform. You have seen this. Tree data structure, read is for catching top queries, horizontal scaling clean, well-understood problem space. Now look at what the same company is asking in 2026 for the same product feature. Design a search and recommendation assistant that understands natural language queries, personalizes results using a user's purchase history, explains its recommendations, and stays within a latency budget of 500 milliseconds and a cost budget of $0.02 per query. Same product. Same user-facing feature. Completely different engineering problem. The 2026 version requires you to think about embedding models, vector search, a ranking layer, a lightweight LLM for explanation generation, and a cost-aware routing layer that decides when to skip the LLM call entirely to stay within budget. Notice what happened. AI components were inserted directly into the core architecture scope. They are not optional add-ons you mention at the end to sound impressive. They are the problem. And if your answer in 2026 is still a tree and a Redis catch, even if it is a perfect tree and Redis design, you have answered the wrong question. That gap between 2024 and 2026 is exactly what this series is designed to close. So what is the single competency that now separates a senior offer from a mid-level offer when the implementation gap has been compressed by AI tools? I will give you the exact answer. It is architecture thinking under ambiguity. Let me unpack that. Architecture thinking means you can look at an underspecified problem and quickly identify the right decomposition, which components carry which responsibilities, where the failure boundaries are, and which trade-offs are load-bearing versus cosmetic. The under-ambiguity part is what makes it hard. A 2026 interview prompt will not tell you whether you need an agent loop or a simple RAG pipeline. It will not tell you the expected query volume. It will not tell you the cost budget. You have to ask, estimate, and justify. And that judgment, that ability to structure chaos into a defensible design under time pressure, is precisely what an AI coding tool cannot do for you. It is also what explains a salary gap that I see routinely exceed 40% between mid-level and senior engineers at the same company, doing work that looks superficially similar. The code looks almost identical. The architecture decisions are completely different. In the next chapter, we are going to do a root cause analysis, specifically why 2026 interview patterns changed this fast, what the industry signals were that most engineers missed, and how to use that understanding to predict what comes next. That context is not background noise. It is the map you need to navigate the rest of this series correctly. Let me be brutally honest with you. In 2023, I watched a junior engineer on my team ship a complete REST API with authentication, pagination, and error handling in under 2 hours using GitHub Copilot, code that would have taken me a full day 5 years ago. That moment is exactly when the hiring signal collapsed. Think about it from a company's perspective. If any reasonably smart person can generate solid implementation code with AI assistance, what exactly are you measuring when you ask someone to write a binary search on a whiteboard? Nothing useful. That's the core problem. F&G and top-tier companies figured this out fast. By late 2024, internal hiring committees started flagging that their LC-style screens were producing false positives, people who could grind leet code but couldn't make a single coherent architectural decision when the rubber met the road, so they shifted to the weight. Implementation skills stopped being a primary signal. System-level judgment became the new bar, and if you're still preparing the old way, you are optimizing for a test that no longer exists. The question is, what exactly replaced it? Teaser, the answer is more specific than you think, and I'll show you the market data to prove it. Now let me show you this isn't just theory, the market data is very real. Byte2Go, which is arguably the most watched system design learning platform on the planet, launched their dedicated generative AI system design course in Q1 2024. Within 90 days, it became their highest viewed content series, outpacing classic URL shortener and Twitter design videos that had been top performers for 3 years straight. That's a demand signal you cannot ignore. On YouTube, architecture videos tagged with LLM system design or AI infrastructure interview saw view counts spike 40% between January 2024 and January 2025. Meanwhile, channels still publishing pure LeetCode content saw flat or declining engagement. And on the interview side, engineers coming out of loops at Google, Meta, Amazon, and Stripe started reporting on Blind and Reddit that they were getting at least one AI component system design question per loop, often two. This isn't an anecdote. This is a structural market shift. The companies that are hiring for the next 5 years of AI-era engineering are explicitly testing whether you can reason about systems that include ML components, vector stores, and inference pipelines. And most candidates walking in are still drawing boxes labeled load balancer and database with no idea what an embedding pipeline even is. Questions, so what are the question categories they're testing? That's where it gets really specific, and you'll want to take notes. Here's the contrast that should make you uncomfortable. The classic system design canon, URL shortener, ride-sharing dispatch, Twitter news feed, those questions were designed for a world where your biggest architectural concern was horizontal scaling of stateless services and relational database sharding. And they're still being asked, but look at how they've mutated. Design a URL shortener is now design a URL shortener with AI-powered spam detection at ingestion time. How does that affect your write path latency? Design Twitter is now design a social feed with an LLM-based content ranking model. Where does inference happen? What's your SLA? And how do you handle model version rollouts without downtime? Same surface question, completely different depth requirement. The engineers who walk in with a memorized template, consistent hashing CDN, read replica, they hit the first layer fine. Then the interviewer asks, okay, now where does your ML model fit in this pipeline? And the candidate freezes. That freeze is the signal the interviewer is looking for. It tells them exactly what they need to know. This person knows the 2019 playbook. They don't know the 2026 system. If you've been drilling classic templates, that's not wasted work, but it's table stakes, not differentiators. Payoff. The real preparation starts with understanding exactly what these 3 new categories look like, and we're going in deep on all 3 right now. Category 1, LM serving system design. This is the one that trips up the most experienced backend engineers because it looks familiar on the surface, but has completely different bottlenecks underneath. A typical prompt I've seen in real interviews: design a system that serves an LM-powered customer support chatbot for a company with 50 million users. The model needs to respond within 2 seconds P99. Sounds like a web service design problem, right? It's not. The moment you accept this prompt, you have to reason about a completely different resource class, GPU compute. Your typical web service scales by adding stateless app servers. LM inference doesn't work that way. GPUs are expensive, non-fungible, and have memory constraints that directly limit your concurrency model. If you don't address that in the first 5 minutes, the interviewer knows you've never actually shipped ML infrastructure. The key scorable dimensions here are 1. Inference latency SLA, where does your P99 budget go? Fulfill VS decode phases have totally different compute profiles. 2. GPU resource planning, how many A100s or A100s do you need at peak and how do you estimate that? 3. Model versioning, when you need to deploy a new model version, how do you do it with zero downtime? And 4. Cost estimation, GPT-4 class inference costs are orders of magnitude higher than a database query. Can you reason about that trade-off under pressure? Teaser, and that's just the serving layer. The next category goes one level deeper into how you actually get relevant data into that LLM in the first place. Category 2, RAG pipeline architecture. RAG, Retrieval Augmented Generation, is now appearing as a standalone system design plan at senior levels. And I want to be very clear about what interviewers are actually testing when they ask this. They're not testing whether you know what RAG is. Everyone knows what RAG is. They're testing whether you understand the failure modes at each stage and the trade-offs you make to address them. Here's a real interview prompt I've heard from engineers post-loop. Design a RAG-based internal knowledge base for a company with 10 million internal documents, supporting 100K concurrent queries, with a freshness requirement that new documents must be searchable within 5 minutes of upload. Walk through how I'd structure this. Stage 1 is document ingestion. You're receiving documents in multiple formats, PDF, DOTX, HTML. You need a parsing pipeline. The chunking strategy is a real design decision. Fixed size chunks lose semantic coherence. Sentence window chunking is better but more expensive to process. Stage 2 is embedding generation. Which embedding model? OpenAI ADA 1002 is easy but creates vendor lock-in and has latency. Open source models like BGE or E5 are cheaper but need infrastructure. Stage 3 is the vector store. Pinecone, Weave8P vector, each has different NN accuracy versus latency trade-offs. Stage 4 is retrieval. Do you do pure vector search, hybrid BM25 plus vector, or re-ranking with a cross-encoder? And stage 5 is the generation call with context injection. The 5-minute freshness requirement is the killer constraint. It forces you to design your ingestion pipeline as a streaming system, not a batch job. That single constraint changes your entire architecture. Question: can you spot what the interviewer is really measuring here? It's not just knowledge, it's whether you reason from constraints to architecture. We'll make that skill explicit in the next category. Category 3, agentic system design. This is the newest category, and it's the one where the gap between prepared and unprepared candidates is the widest right now. I've talked to hiring managers at 3 different top-tier companies in the last 6 months, and all 3 told me the same thing. When they ask an agentic architecture question, most senior candidates stare at them like they just spoke a different language. So let me make this concrete. An agent in the system design context is not just a chatbot. It's a program that can autonomously decide which tools to call, in what order based on intermediate results, and loop until it reaches a goal or hits a termination condition. The architectural question is, how do you build the infrastructure around that loop? Let's break it down. The agentic loop itself is a planning execution cycle. Receive goal, break into subtasks, call tools, observe results, replan, repeat. That loop needs to be fault tolerant. What happens when a tool call fails mid-execution? You need state persistence so the agent can resume. The tool registry is a critical component. It's essentially a catalog of callable APIs with schema definitions that the orchestrator uses to select the right tool for each step. Multi-agent coordination adds another layer. You have a supervisor agent delegating to specialized subagents. Now you need a message bus between them, conflict resolution when agents produce contradictory outputs, and observability across the entire execution graph. And here's the interview killer question. How do you prevent infinite loops in your agentic system? If you don't have a concrete answer, max step limits, cost budget caps, human-in-the-loop checkpoints, you fail at round regardless of everything else you said. The companies building AI products today have this problem in production. They need engineers who've already thought it through. Payoff: now you understand the 3 categories. But knowing the categories isn't enough. You need a structured framework to attack any one of them in 30 minutes under pressure. That's exactly what Chapter 3 is going to give you, a repeatable thinking structure that works whether the question is RAG, agentic, or anything that hasn't been invented yet. All right, let's talk about the first 3 minutes of your interview, because that's where most candidates already lose. I've watched dozens of engineers jump straight into drawing boxes on the whiteboard. API gateway here, database there, done. And the interviewer writes a shallow in their notes before you've even picked up the marker. Here's the real trap. In 2026, interviewers are deliberately leaving AI requirements unstated. They want to see if you surface them. So layer 1 is requirement scoping, and it's not just asking how many users. You need to ask, is there a personalization component? Does ranking need to be ML-driven? What's the acceptable latency for model inference? These are the questions that signal senior-level thinking. Lock scope in 3 minutes, and you control the entire interview narrative. But here's what nobody tells you. The way you ask these questions matters just as much as the questions themselves. I'll show you exactly how in the next scene. Now, layer 2, the high-level component map. And I want to destroy one myth right now. You do not start by drawing your database. I see this constantly. Engineers draw the DB first because it feels safe and familiar. Wrong move. You start at the API gateway, because that's where the client contract lives, and you trace the data flow forward. Client hits the gateway, auth happens, request routes to the appropriate service, service talks to storage, and this is the 2026 edition that separates candidates. You explicitly insert the AI processing layer, not as an afterthought, not as a box labeled ML magics in the corner. You show where inference happens in the request path, what it reads, and what it writes. The sequence on the whiteboard matters. Interviewers watch your drawing order as a proxy for your mental model. A senior engineer traces causality, data flows from left to right, time flows top to bottom. Master this sequence, and your diagram tells a story even before you speak. But choosing which component to zoom into next, that's a completely different skill, and most candidates get it wrong. Layer 3, deep dive selection. This is where good candidates stall and great candidates accelerate. After your high-level diagram, the interviewer will either ask a specific question or they'll go silent. That silence is a signal. They're waiting to see which component you choose to drill into. Here's the pattern I've seen across top-tier interviews in 2024 and 2025. If your system has an AI component and you deep dive into the database sharding strategy instead, you've just told the interviewer you don't understand what's actually hard. The expected deep dive target in 2026 is the AI-related bottleneck, the inference pipeline, the embedding generation latency, the model serving infrastructure. Watch for these cues. The interviewer leans forward, they ask how does that work exactly? Or they repeat a keyword you mentioned. Those are green lights. The interviewer crossing arms or saying interesting and what else means pivot. Read the room. But even if you pick the right component, saying the wrong thing about trade-offs will kill your score. That's layer 4 coming up next. Layer 4, explicit trade-off declaration. Let me give you the single most impactful sentence structure used in a system design interview. I'm choosing X over Y because of Z, and the cost I'm accepting is WD. That's it. That's the formula. Junior engineers present a solution. Senior engineers narrate a decision. Here's a real example. I'm choosing eventual consistency over strong consistency here because our AI recommendation pipeline can tolerate a 500-gem staleness window, and the trade-off is that a small percentage of users will see slightly stale recommendations, which is acceptable given our product requirements. You've just demonstrated systems thinking, product awareness, and CAP theorem understanding in one sentence. The compare slide behind me shows the most common trade-off pairs that come up when AI components are involved. Consistency vs availability is table stakes. Every candidate knows this. What separates you is articulating cost versus latency in the context of model inference. Strong consistency on your vector store versus faster approximate retrieval. That's a 2026 question. Gets layer right, and you signal architect-level thinking. Now let's look at how to actually plug an AI component into any system design. Here's the reusable pattern I want you to memorize, because you can drop into any system design question that involves AI. Whether it's a recommendation system, a search product, a customer support bot, the AI component placement question is always the same. Does the model sit in the synchronous request path, or does it live outside it? This is not a philosophical question. It's a latency budget question. If your total user-facing SLA is 200 milliseconds and your model inference takes 80 to 150 milliseconds, you have almost nothing left for network, auth, and storage. That math tells you the AI should be async, pre-compute, or post-process, not inline. But there are cases where inline inference is correct. Fraud detection, content moderation, real-time personalization of the first page load. The rule I use, if the model output gates the response, it must be synchronous. If the model output enriches the response, make it async. And always, design the fallback first. What does your system return when the model is down or times out? I've seen production incidents where nobody thought about this, and the entire product returned empty results for 4 hours. Design the fallback before you design the happy path. Now let's look at the specific pattern for RAG systems, because that's what half of 2026 interview questions are actually testing. RAG, Retrieval Augmented Generation. If you don't have this pattern memorized by your next interview, you are walking in underprepared. It is now the default architecture for any AI-assisted search, Q&A, or knowledge system question. And interviewers test not just whether you know RAG exists, but whether you understand the engineering problems inside each layer. Let me walk you through the 4 layers. First, the embedding catch. Generating embeddings is not free. It costs compute time and API money. If the same query comes in repeatedly, you should catch the embedding, not regenerate it. Use a hash of the normalized query as the catch key. Second, the vector store retrieval. You're doing approximate nearest neighbor search here, HNSW index, cosine similarity, top K results. Know your numbers. Sub-10 retrieval is achievable at scale with proper indexing. Third, context assembly. You're taking K retrieved chunks and assembling them into a prompt. This is where context window management becomes critical. You cannot blindly concatenate. You need a ranking and truncation strategy. Fourth, prompt construction. Template management, system prompt versioning, and token budget allocation before you ever call the LLM. Each of these layers has failure modes. The interviewer who asks about RAG is really asking, do you know where it breaks? The agent loop pattern takes this even further, and that's exactly what breaks in ways most engineers don't anticipate. Now, the agent loop, and this is where I see the biggest knowledge gap in 2026 interviews. Most candidates know what an agent is conceptually. Almost none of them can diagram one correctly under interview conditions. Here's structure. An agent loop is a stateful, iterative process. It has 4 core components: the tool registry, the execution sandbox, the result aggregator, and the handoff to the user-facing response layer. The tool registry is just a catalog of callable functions: web search, code execution, database query, API call. The agent decides which tool to call based on the current state. The execution sandbox is where those tool calls actually run, isolated with timeouts and resource caps. Because agents running unconstrained will absolutely abuse your infrastructure. I've seen this in production. An agent got into a loop calling an external API 40,000 times in 90 seconds. Design the sandbox with hard limits. The result aggregator collects tool outputs across multiple iterations and maintains state. This is your state management problem. Where does the intermediate state live? In memory? In Redis? In a database? And finally, the handoff layer. When does the loop terminate? And how does the result get back to the user? Streaming response or batch? These questions will come up. Now that you have the patterns, let's talk about the dimension that top-tier companies added to their rubrics in 2025, cost estimation, and it will surprise you how much it weighs in the scoring. I need to tell you something that most interview prep resources are not saying yet. Top-tier companies, and I'm talking about the ones that pay $300,000 to $500,000 in total compensation, added cost estimation to their system design scoring rubrics in 2025. It is now an explicit evaluation dimension, not a nice-to-have, not a bonus point, a dimension. I've spoken with engineers who came out of these loops, and they said the interviewer literally asked, what do you estimate the monthly infrastructure cost of this system would be at the scale you described? And the candidates who said I'd have to look up the pricing lost points. The candidates who said roughly this number, based on these assumptions, even if the number was off by a factor of 2, passed. Why? Because the number itself matters less than demonstrating that you think about cost as a design constraint from the beginning. The table behind me shows a simplified version of what these scoring rubrics look for. Notice that cost awareness is weighted equally with scalability in some rubrics. This is new. This is the 2026 shift, and the calculation is not as hard as you think. Let me show you the exact arithmetic. Okay, let's do the math live. This is the back-of-envelope calculation you should be able to verbalize in under 2 minutes during an interview. Scenario: you're designing an LLM-powered content recommendation system, 1 million daily active users. Each user generates 2 AI-assisted requests per day. That's 2 million LLM calls per day. Now each call, let's say 500 tokens input, 200 tokens output, 700 tokens total. 2 million calls times 700 tokens equals 1.4 billion tokens per day. At current GPT-4 class pricing of roughly $2 per million tokens, that's a blended estimate, you get $2.8 thousand per day. Multiply by 30, approximately $84,000 per month in inference cost alone. That number immediately triggers your optimization instincts: semantic catching to eliminate duplicate queries, smaller models for simple requests, batching to improve GPU utilization. The code on this slide shows the exact calculation as pseudocode you can narrate while writing on a whiteboard. Interviewers don't expect precision. They expect structured thinking. The candidate who says roughly $80K per month, here's why, and here are 3 levers to reduce it, is the candidate who passes. Here are those 5 levers, and 2 of them consistently surprise interviewers who don't expect candidates to know them. $100,000 a month. That's the number that triggers the next question every time. How would you reduce that cost? And this is where you show architectural sophistication, not just operational awareness. There are 5 levers, and they have a priority order. First, semantic catching. If 30% of your queries are semantically similar, and in recommendation systems they often are, you eliminate that 30% of LLM calls entirely. Embed the query, hash the embedding, check catch before calling the model. Second, request batching. GPU inference is dramatically more efficient when you batch multiple requests together. A batch of 16 requests uses roughly the same GPU compute as a batch of 1. Your throughput goes up, your cost per request goes down. Third, model quantization. NT8 inference instead of FP30T2 gives you roughly 2 times the throughput at 70 to 80% of the cost, with less than 2% accuracy degradation for most recommendation tasks. Fourth, tier-based model selection. Not every request needs a frontier model. Simple queries route to a small model, 7B parameters, fast, cheap. Complex or ambiguous queries escalate to the large model. The routing logic itself is a system design question. Fifth, async offloading. Non-real-time workloads, batch recommendation refresh, report generation, get moved to spot instances and scheduled off-peak. This one alone can cut 20 to 30% of your GPU bill. Interviewers who know AI infrastructure will nod when you hit quantization and tier-based routing. Those 2 signal real depth. And now that you have the full framework, layer 1 through 5, A component patterns, cost estimation, the next chapter puts it all together in a live walkthrough of an AI-powered content recommendation system. You'll see every one of these concepts applied in real time in sequence under interview conditions. That's where the framework becomes muscle memory. All right, let's do a real live walkthrough. The interviewer just said, design an AI-powered content recommendation system. That's it. Full stop. And here's where most candidates immediately grab the marker and start drawing boxes. That's the trap. I've watched dozens of engineers tank interviews in the first 3 minutes by skipping clarification. The first 5 minutes are not for drawing, they're for interrogating the problem. So here are the exact 6 questions I ask every single time in this order. First, what type of content are we recommending? Articles, videos, products? Second, what is the primary optimization target? Click-through rate, watch time, or purchase conversion? Third, what is the expected DAU and how many recommendations per session? Fourth, do we have an existing user item interaction history, or is this a greenfield system? Fifth, what is the acceptable end-to-end latency for a recommendation API call? And the sixth one, this is the 2026 specific question that almost nobody asks. Do you expect an LLM component in this design, or is a classical ML pipeline acceptable? That last question tells you everything about what the interviewer actually wants to evaluate. Some interviewers want to see if you know when not to use an LLM. Coming up, I'll show you what the numbers actually look like once you get those answers. Good. Let's say the interviewer gives you these answers: 50 million DEU, video content platform, 10 recommendations per page load, PNA9 night latency under 200 milliseconds, and yes, include an LLM ranker component. Now you do the math out loud. This is not optional. Doing the arithmetic in front of the interviewer is how you demonstrate systems thinking. Here's how I work through it. 50 million DAU. Assume users are active across 16 hours a day. That's a realistic waking hour distribution. 50 million users, average 3 page loads per session, 10 recommendations each. That gives you 1.55 billion recommendation requests per day. Divide by 86,400 seconds, you land at roughly 17,400 requests per second at average load. Now peak traffic. Assume a 3x multiplier for prime time. That's about 52,000 RPS peak. For write throughput, user events like clicks, watches, skips, assume 20 events per user per day. That's 1 billion events per day, roughly 11,500 writes per second. For embedding storage, 50 million users, each with a 256-dimensional flow 32 embedding. That's 50 million times 1 kilobyte, roughly 50 gigabytes just for user embeddings. Add item embeddings for 10 million videos at the same size, another 10 gigabytes. Total vector store footprint, approximately 60 gigabytes before replication. These numbers now govern every architectural decision you make. Notice how this instantly rules out naive solutions. This is what senior thinking looks like. Now we explicitly draw the system boundary. This step is where I see mid-level engineers blur the scope and spend 20 minutes designing something nobody asked for. The system boundary conversation is a 2-minute verbal contract with your interviewer. Here is the API contract for this system. Input, a user ID, an optional context string, what they're currently watching or reading, and a requested count of n recommendations. Output, an ordered list of content IDs with relevance scores and an explanation token for observability. Now the non-functional requirements, specifically for the AI component, and this is different from general NFRs. Recommendation freshness. User behavior from the last 30 minutes should influence recommendations. That's a real-time feature freshness requirement. Model staleness tolerance. The base embedding model can be retrained weekly. That's acceptable drift. LLM ranker latency budget. Within the 200 ms total SLA, we can allocate at most 80 ms to the LLM ranker. That constraint alone tells you which LLM models are feasible. You're not calling GPT-4 at that latency. And finally, the AI component must degrade gracefully. The LLM ranker times out, fall back to the classical ranking score. Explicit fallback behavior is not optional in production. When you define boundaries this precisely in an interview, you signal that you've shipped real systems. The next section is where we actually build this thing layer by layer. Okay, now we draw. And here is the single most important discipline in a live design session. Build the diagram incrementally, narrating each component as you add it. Never draw the full diagram in silence and then explain it. That is a guaranteed way to lose the interviewer. I build it in 5 stages. Stage 1, user event ingestion. User clicks, watches, skips, all of these fire events to an ingestion API, which immediately publishes to a Kafka topic. I keep this dead simple because reliability here is non-negotiable. Stage 2, the feature store. A Flink streaming job consumes from Kafka and updates a feature store. I'd use Redis for real-time features like last 10 videos watched in this session, and a columnar store like Cassandra for slower-moving features like genre affinity over 30 days. Stage 3, the embedding service. This is a dedicated microservice, not part of the recommendation API, that takes user features and generates a user embedding vector. It reads from the feature store, calls a pre-trained embedding model, and writes the result to a vector database. I keep this async and decoupled. Stage 4, vector retrieval. When a recommendation request arrives, we query the vector DB with the user's current embedding using approximate nearest neighbor search. This gives us a candidate set, typically 500 to 1,000 items, in under 20 milliseconds. Stage 5, the ranking model. A lightweight, gradient-boosted model, something like XGBoost, takes the ANN candidates plus real-time features and scores each one. This is your primary ranking layer before we even touch LLMs. Why 5 separate components? Because each one has a different scaling dimension, a different failure mode, and a different team ownership boundary in real organizations. But wait, we haven't added the LLM yet. That's the next scene, and the reason matters more than you think. Now let's talk about where the LLM actually lives in the stack and more importantly, where it does not live. This is the question that separates 2026 senior engineers from everyone else who just slapped GPT-4 onto their diagram. The LLM ranker is a late-stage optional component. It operates after the classical ranking model has already produced a shortlist, say the top 50 candidates. It does not touch the retrieval phase. It does not replace the ANN search. If you put the LLM earlier in the pipeline, you've just made a system that cannot meet a 200 millisecond SLA at any scale. So when do you use LLM re-ranking? 3 conditions must be true simultaneously. 1. The business metric you're optimizing, watch time, conversion, shows measurable lift from semantic understanding that the gradient-boosted model cannot capture. 2. The cost per request is acceptable given your margin. At 50,000 RPS peak, even in a 0.5 LLM call per request becomes $25,000 per hour. 3. You have the latency budget. Remember, we allocated a maximum of 80 milliseconds. That means you're calling a small, fine-tuned model, a 7B parameter model served on a GPU cluster, not a frontier API. The personalization layer here is the context injection. You pass the user's recent watch history, the current session intent, and the top 50 candidate titles to the LLM. It returns a reordered list with a brief rationale. The rationale is not for the user, it's for your debugging and observability pipeline. Here's the hard truth from production. In 80% of cases, the classical ranking model with fresh features outperforms LLM ranking on your core business metric at 1/100th of the cost. Your interviewer wants to know if you know that. The data pipeline design is where I see the most architectural debt in production recommendation systems, and it's also where interviewers probe hardest in 2026. Let me walk you through the design decision that matters most, real-time versus batch, and when you need both simultaneously. The event stream path, user events land in Kafka with a retention of 7 days. You want replay capability. A Flink job consumes events with exactly once semantics and writes to 2 destinations. The real-time features store in Redis for session-level features. These need to be fresh within seconds. And an event lake in S3 or GCS in Parquet format for batch processing. Now the batch path, every 4 hours, a Spark job reads from the event lake and recomputes heavy features, genre affinity scores, user cohort memberships, content popularity decays. These are too expensive to compute in the stream. The embedding refresh schedule, user embeddings are regenerated every 6 hours for active users, weekly for dormant users. Item embeddings for new content are generated within 15 minutes of upload. That 15-minute SLA for new content embeddings is a real operational challenge that most candidates never mention. Here is a critical architectural insight about feature freshness. Your recommendation quality is directly bounded by your stylist feature. If your session features are 5 minutes stale during a traffic spike, because Redis is under pressure, your recommendations degrade silently. This is why I build a feature freshness monitoring system, a separate service that tracks P99 write latency to Redis and emits an alert if feature lag exceeds 60 seconds. Most candidates design the happy path. Senior engineers design the degradation paths. The next section is where we go deep on the hardest component choices, and I'll show you exactly how to defend your decisions. Now we go deep on the component most interviewers will probe in 2026, the vector search layer. And the question they will ask you is HNSW or IVF. If you don't have a crisp, reasoned answer, you've just signaled you've only read about vector search, not operated it. Let me give you the exact framework I use. HNSW, Hierarchical Navigable Small World, is a graph-based index. It builds a multi-layer proximity graph during indexing. At query time, it navigates this graph greedily to find approximate nearest neighbors. The strengths, extremely high recall at low latency, typically above 95% to recall at under 10 milliseconds for a 10 million item corpus. The cost, memory. HNSW holds the entire index in RAM. For our 60 gigabyte vector store, that's a significant memory footprint per node, and it scales with corpus size. IVF's inverted file index partitions the vector space into Voronoi cells using means clustering. At query time, you search only the nearest end cells rather than the full space. The strength, dramatically lower memory footprint and better suited for extremely large corpora, hundreds of millions of items. The cost, recall drops as you reduce the number of cells you probe. There's a recall versus query time knob you tune with the probe parameter. So which one do I choose for this system? HNSW. Here's my explicit reasoning. Our corpus is 10 million video items. At 1 kilobyte per embedding, that's 10 gigabytes, well within what a single high memory instance can serve. Our latency SLA for retrieval is under 20 milliseconds. HSWD gives us 97% to recall at 8 milliseconds, comfortably within budget. The corpus grew to 500 million items. I'd migrate to IVF with product quantization. I state the scaling trigger explicitly. That last sentence is what makes the difference between a senior and a principal level answer. Here's the architectural foresight test. The interviewer hasn't asked you about cold start yet, but you bring it up yourselves. That single move, proactively surfacing an edge case before you're prompted, is one of the clearest signals that distinguishes a senior engineer from a mid-level engineer in a design interview. So let me show you exactly what you say and how you handle it. Cold start has two distinct forms, and they require different solutions. Form 1, new user cold start. The user just created an account. They have zero interaction history. Their user embedding doesn't exist yet. If you query the vector DB with a null embedding, you crash or return garbage. The naive fix is to serve popularity-based recommendations, the top trending videos globally. This works but introduces popularity bias that makes your recommendation system less diverse over time. The better approach is a brief onboarding interest selection, 3 to 5 category preferences, which seeds an initial user embedding by averaging the embeddings of items in those categories. This gives you a meaningful starting point with a single user action. Form 2, new item, cold start. A creator just uploaded a video. The item embedding hasn't been generated yet. Our pipeline says 15 minutes for new content, but for the first 15 minutes, this item is invisible to the recommendation system. The solution is a content-based metadata embedding generated synchronously at upload time using title, description, and tags, which is a cheap operation that takes under a second. This placeholder embedding gets you into the index immediately, and the full model-based embedding replaces it after the async pipeline completes. Notice what I did there. I didn't just identify the problem. I gave a concrete, implementable solution for each variant. That's the difference between describing a problem and demonstrating you've solved it before. Let's close this design with something almost nobody does in a system design interview, a real cost estimate, and I mean a real one, with numbers you can defend, not hand-wavy. It depends on the cloud provider evasion. And in 2026, cost awareness is a hard requirement for senior-level evaluation. Let me walk through the 3 major cost centers. First, embedding generation. We have 50 million active users, each getting their embedding refreshed every 6 hours. It's roughly 200 million embedding regeneration calls per day. Using a self-hosted sentence transformer model on GPU, a single A10G GPU at 50 cents per hour can process approximately 5,000 embeddings per second at 200 million per day. That's about 11 GPU hours per day, roughly $550 per day, or about $165 per month just for user embeddings. Add item embeddings for new content uploads, negligible by comparison. Second, vector database hosting. 60 gigabytes of vector data, triple replicated on a managed vector DB service. Approximately $800 to $200 per month depending on provider. Third, the LLM ranker. This is the expensive one. At peak 50,000 RPS, even if only 20% of requests use the LLM ranker, a reasonable rollout percentage, that's 10,400 LLM calls per second. A 7 billion parameter model served on A10G GPUs can handle about 50 requests per second per GPU. You need approximately 200 GPUs just for LLM ranking at peak. At 50 cents per GPU hour, that's $2,400 per hour at peak, or roughly $864,000 per month if you run peak load continuously. That number is why the LLM ranker is a 20% to roll out. In production, you A/B test it rigorously against the classical ranker before expanding. This is the system design answer that gets you the offer. Next chapter, I'll share the war stories, the production failures, and interview moments that shaped every decision I've shown you today. Here's a pattern that surfaces constantly in system design interviews: a candidate with 8 years of experience, strong resume, clearly smart. The problem? Design a notification system for a 10,000 DAU internal tool. Within 2 minutes, he was drawing Kubernetes multi-region clusters, Istio service mesh, Kafka with 3 broker replicas, and a separate microservice for each notification channel. The interviewer stopped him and asked, "Why multi-region?" He said, "For high availability." I asked, "What's your SLA?" He paused. He didn't know. Here's the brutal truth. Senior engineers on interview panels don't reward complexity. They penalize it. Because in production, unnecessary complexity kills teams. Every abstraction layer you add is a future on-call incident waiting to happen. A monolith with a message queue handles 10K DU perfectly fine. The moment you propose Kubernetes for a system that fits in a single EC2 instance, you've already failed the judgment test. Sophistication is not the goal, fitness for purpose is. But weight over engineering is obvious in hindsight. What about the mistakes that are invisible until production blows up? Now here's where it gets real. This one happened to my own team. We were building an AI writing assistant feature. Product said latency under 2 seconds. Engineers were excited, shipped fast. The architecture? User hits the endpoint. Endpoint calls GPT-4 synchronously, waits for the full response, then returns to the user. Looked fine in staging with 5 concurrent users. Week 1 in production. P50 latency 1.8 seconds acceptable. But P99. 11 seconds. Our SLA was 2 seconds. On-call gets paged at 2 a.m. We look at the traces. The LM call is sitting directly in the hot path, blocking the entire request thread. When upstream had any hiccup, requests stacked up. Thread pool exhausted. Service degraded completely. The fix wasn't complicated. We moved the LM call to an async worker. User submits request, gets a job ID immediately, polls or receives a webhook when results are ready. P99 dropped to 400 ms for the acceptance phase. The LM still takes the same time, but the user experience is completely different. The lesson: never put a non-deterministic external API call in a synchronous hot path, ever. And this mistake is now explicitly tested in 2026 AI system design interviews. The cost mistake that follows this one is even more expensive. All right, the latency incident was painful. This next one was financially catastrophic, and it's the type of incident that has become a standard evaluation criterion at major tech companies. A team launched an AI summarization feature. Conservative usage estimate: 50,000 requests per day, average 500 tokens per call. Product did the math, finance approved the budget. Week 1 goes live. Usage is higher than projected, great problem to have, right? Wrong. Nobody had implemented any token budget controls. No rate limiting per user. No prompt length caps. No catching for identical inputs. Users were submitting the same document 5 times because the UI had a bug causing duplicate submissions. One power user sent a 32,000 token context document 200 times. By day 7, the team had burned 40 times their monthly budget. The CTO called an emergency meeting. The feature was disabled while the architecture was hardened. The fix required per-user token quotas, input length validation, semantic catching with embedding similarity matching, and a cost dashboard with automated circuit breakers. Now here's why this matters for your interview. In 2026, any AI system design problem that doesn't include cost governance is considered incomplete. Full stop. If you don't mention token budgets and cost circuit breakers, the interviewer marks you down. Coming up next, we'll flip to the interviewer's side of the table and show you exactly what they're scoring. Let me show you the actual scoring dimensions that staff engineers and principal engineers use when evaluating system design rounds. This reflects what the industry consistently reports matters in debrief discussions. Technical correctness still matters, but it's table stakes. What separates a strong hire from a no hire in 2026 is how you handle the things that aren't in the problem statement. Ambiguity navigation: does the candidate ask clarifying questions that reveal systems thinking, or do they immediately start drawing boxes? Proactive risk surfacing: do they identify failure modes before the interviewer has to prompt them? Cost and operational awareness: do they mention monitoring, alerting, runbook considerations? AI-specific judgment: do they know when to use an LLM, and do they account for non-determinism? The candidates who score highest aren't the ones with the most sophisticated architecture. They're the ones who think out loud like an engineer who has actually operated systems at scale. Here's the uncomfortable question: are your clarifying questions revealing systems thinking, or just stalling for time? Let's look at what that communication pattern actually looks like. Same problem, 2 candidates. Both are technically competent. Watch what happens. Candidate A: they go quiet for 2 minutes, then present a complete, polished architecture. Everything is labeled. The design is actually solid. But when the interviewer asks, why did you choose Cassandra over DynamoDB here? Silence. Then a vague answer about right performance. The candidate had made the decision privately, hadn't articulated the trade-offs, and now can't reconstruct their own reasoning under pressure. Candidate B: from minute 1 they're talking. I'm thinking about read versus write ratio here. If this is read heavy, I'd lean toward a caching layer. But if writes dominate, I want to think about write optimized storage. When they hit a trade-off, they name it out loud. I could go Cassandra for the write throughput, but then I'm giving up ASI guarantees. For this use case, I think that's acceptable because the interviewer is nodding the entire time. Not because candidate B's design is better. It might not be. But the interviewer can see exactly how this person thinks, and that's what they're hiring: the thinking, not the diagram. The diagram you can Google, the judgment you cannot. And here's where it gets interesting. This communication pattern changes significantly depending on which market you're interviewing in. Last point in this chapter, and this one is specifically for anyone targeting Korean enterprise or large tech companies domestically. The interview format is fundamentally different, and candidates trained on LeetCode and US-style whiteboard prep get blindsided by it. In US-style system design interviews, the output is a conversation and a whiteboard sketch. The diagram is a communication tool, not an artifact. Korean enterprise technical interviews, especially at the large conglomerates and Korean big tech companies, often require a written design document. You sit down, you produce a structured artifact. This might include a requirements section with functional and non-functional specs written out, a component diagram with written justification for each choice, a data model section, an API contract sketch, and a section on failure modes and mitigation. The evaluation isn't just to get the right answer, it's is this document coherent enough that another engineer could implement from it. This is actually closer to how senior engineers operate in real production environments. If you're targeting these companies, practice producing a one-page design doc under time pressure, not just drawing boxes. And with that, we've covered every major failure mode and scoring pattern you need to understand. Next chapter is where it all lands. Your specific do's and don'ts, and a 30-day action plan to actually build these skills before your next interview loop. Let me be blunt. Based on patterns that appear repeatedly across system design interviews, the difference between mid-level and senior-level thinking becomes clear within the first 3 minutes. It's not about knowing more technologies. It's about 7 specific anti-patterns that candidates repeat over and over, and they don't even realize they're doing it. Anti-pattern number 1, designing without any cost awareness. You draw a beautiful microservices diagram with 5 Kafka topics and 3 L inference endpoints, and the interviewer asks, "What's the monthly cloud bill?" And you freeze. That's an immediate signal. Anti-pattern 2, ignoring failure modes entirely. You describe the happy path perfectly, but never mention what happens when the vector database goes down or when the LLM API times out at 29 seconds. Real systems fail. Senior engineers design for failure first. Anti-pattern 3, underspecifying AI component boundaries. You say we'll use an LLM here without defining latency SLA, fallback behavior, prompt versioning strategy, or output validation. That's not architecture, that's a wish list. Anti-pattern 4, jumping to technology before clarifying requirements. You say let's use Kafka before you even know the right throughput. Anti-pattern 5, treating scalability as infinite. We can just add more nodes. Anti-pattern 6, no mention of observability. If you can't measure it, you can't operate it. Anti-pattern 7, zero cost trade-off narration. You make decisions but never explain why. Each of these screams mid-level. And the painful part? Most candidates with 5 to 8 years of experience fall into at least 4 of these traps. Coming up next, I'll show you the exact senior engineer countermove for each one. Now let's flip every single one of those anti-patterns and look at what a senior engineer actually does, because the difference isn't just knowledge, it's a completely different operating mode during the interview. Take anti-pattern 1, cost blindness. The senior engineer move is to proactively anchor cost early. You say something like, before I finalize this design, let me do a rough cost sanity check. If we're handling 10 million inference calls per day at roughly 2 per call, that's 20,000 per day, 600K per month. That changes our catching strategy significantly. That one sentence tells the interviewer you've run real production systems with real budgets. For failure modes, the senior move is to design the degradation ladder before the happy path. You say, let me define 3 operating states: full capability, degraded with cached responses, and minimal fallback. Now let me show how the system transitions between them. For AI component boundaries, the senior signal is specifying contracts, not just components. You define latency P99 budget, token limit per request, output schema validation, prompt version pinning, and A/B testing hooks. That's a deployable AI component, not a prototype. For requirement clarification, you ask exactly 5 scoping questions in the first 2 minutes: scale, consistency requirements, latency SLA, budget constraint, and team size. For observability, you name your 3 golden signals and which dashboard tool you'd use. The pattern here is not just knowing more, it's narrating your judgment out loud. Every decision comes with a because and an instead of. That narration is what separates senior from mid-level in the eyes of an interviewer. The moment you adopt this operating mode, your entire interview trajectory changes, and I'll show you exactly how to practice this in 30 days. I've seen engineers spend 6 months preparing for system design interviews by reading blog posts and watching YouTube videos and still fail. The problem isn't time, it's structure. So let me give you the exact 30-day sprint I would run if I were job hunting tomorrow. Week 1 is framework internalization. You're not practicing problems yet. You're drilling the mental model, the 5-step clarification protocol, the cost estimation heuristics, the failure mode taxonomy. Every day you pick one real production system: Instagram's feed, Stripe's payment pipeline, Uber's dispatch system, and you reverse engineer it using the framework. Write it down. Time yourself. Week 2 is AI component pattern drilling. This is where 2026 prep diverges from every outdated guide out there. You spend this week specifically on RAG pipeline design, LLM gateway architecture, vector database selection trade-offs, and agent orchestration patterns. You're building a mental library of AI component contracts so that when an interviewer says add a recommendation engine, you already have 3 design options loaded with their cost and latency profiles. Week 3 is live mock interviews. Not solo practice, live with another human with a timer running. Use a partner, use a service, use your team. Record every session. Watch it back. You will be horrified the first time. That horror is growth. Week 4 is cost estimation practice and documentation. You spend this week building your personal cost estimation cheat sheet: GPU inference pricing, vector DB storage costs per million embeddings, CDN egress rates. You also write up 3 architecture case studies as if you were documenting them for a new team member. That documentation discipline becomes your interview narration discipline. 4 weeks, 4 distinct skill layers. This is not optional if you want to pass a senior level loop in 2026, and the specific resources to fill each week are coming right now. Let me be very specific about resources, because the landscape is littered with outdated material that will actively hurt your 2026 prep. Here's the stack I actually recommend, layered by purpose. At the foundation level, designing data-intensive applications by Martin Kleppmann is still the non-negotiable baseline. Everything else sits on top of it. But here's what's changed. The middle layers are where most candidates fail. For AI-era architecture patterns, you need the AWS Well-Architected Framework for Machine Learning, the Andreessen Horowitz AI Canon Reading List, and the LangChain and the LeMaindex production case studies, not the tutorial docs, the production postmortems. For cost estimation practice, the AWS and GCP pricing calculators are your daily tools, but more importantly, read the architecture blogs from Figma, Notion Discord, and DoorDash Engineering. They publish real cost breakdowns from real production migrations. For practice problems, the system design interview books by Alex Su are still useful for Volume 1 patterns, but Volume 2 is getting stale. Supplement with the Hello Interview platform and the Exponent mock library. They've updated their question banks for AI system components. What's now outdated and harmful? Any resource that treats add a load balancer as the climax of scalability thinking, any guide that doesn't address AI inference cost as a first-class constraint, and any mock interview that doesn't score you on trade-off narration. Delete those bookmarks. The resources that will actually differentiate you treat architecture as a financial and operational decision, not a technical puzzle, and that mindset is exactly what the final takeaways are about. We've covered a lot of ground across 6 chapters, from the 2020-26 interview pattern shift to AI component architecture, to war stories from real production systems and real interview rooms. Let me leave you with 3 non-negotiables. These aren't tips. They are the new minimum bar for senior engineer evaluation. First, architecture thinking is the new implementation skill. AI is writing the code. What AI cannot do is make the trade-off decision between a synchronous RAG pipeline and an async pre-computation catch when the cost profile changes. That judgment, that is your irreplaceable value. Protect it, develop it, and demonstrate it explicitly in every interview. Second, cost estimation is now scored explicitly. This was implicit for years. Interviewers would note it but not score it. In 2026, it's a first-class evaluation criterion at companies like Google, Meta, Stripe, and every AI-native startup. If you cannot do a back-of-envelope GPU inference cost estimate, you will not pass the senior loop. Full stop. Third, proactive trade-off narration is what separates senior from mid-level. The candidate who makes great decisions silently looks exactly the same as the candidate who got lucky. The senior engineer narrates the decision. I'm choosing eventual consistency here because the write latency budget is tighter than the read staleness tolerance, and here's the operational implication. That narration is your proof of work. 30 days from now, if you've run this sprint, you won't just be better at system design interviews, you'll be a better engineer, because the discipline of designing for cost, failure, and observability from day one is what production systems actually demand. Go build something hard, measure everything, and come back with war stories of your own. That's how you become the person giving this lecture.